Florida has the most shoreline in the continental U.S. Because of that, we have a lot of eroding shorelines, especially related to sea level rise. In terms of shoreline restoration, it's just such a major need in Florida with climate change and all of the storms that our shorelines face.
We're really trying to think about all those frequent but smaller scale storms that kind of eat away at that shoreline, which then increases the vulnerability when that bigger event comes.
I get a lot of questions and concerns about sea level rise, especially with all the storms that we get. I decided that, having a visual project that shows people what a living shoreline can do, how it can improve an area, is really what motivated this project.
There are a lot of people that are seeing their shorelines go away, and so what we're trying to do here with these living shoreline projects is show people what's possible and give them a system that they can come and visit so they can visualize some more ecologically friendly options that are also lower cost.
What we want to have is a shoreline. When the wave comes in, it gets absorbed. It either runs up a beach, loses its energy that way, or more importantly, we run it into oyster reefs. We run it into vegetated shorelines, and all that basically starts to consume the energy that otherwise was in that wave, so that by the time it actually gets to that infrastructure, there's no real energy left.
You're going to have that reduction in wave energy and have sediment accretion going on, and then eventually you're going to have salt marsh grass moving in. That's going to really create a nice stabilization for your shoreline.
Here in Cedar Key, we have lots of demonstration projects, but we actually are expanding statewide in terms of our demonstration areas, especially based around a new material that we call reef prisms. And they are an exciting alternative to shell bags, which are plastic bags that use oyster shell. It's a common material in living shorelines. And so statewide, we are trying to test out these reef prisms as a new living shoreline material that can help practitioners move away from using plastics while also accomplishing their oyster restoration and living shoreline goals.
This park, Goffinsville, is a great example of they had a huge erosion problem due to storms, due to the fast current, and so they had to build this very large seawall here. And so today we're trying to show that you can also stabilize the shoreline, not having to use seawalls, but really implementing these living shorelines.
There's a really big need to restore and bolster our shorelines, and to the extent possible, using environmentally friendly or ecologically sound approaches are preferable to building walls and putting out rocks whenever we can.
Here locally, we have this project going on, but there's a lot of discussion happening on Amelia Island, and they're trying to implement some of these living shorelines on their downtown space to also create more awareness and education about them.
Along this shoreline, we have some artificial oyster substrate. These breakwaters are one type of commercially available structure, and then we've got the sand and the vegetation that all are part of a living shoreline. So we have projects that are essentially in line with that all over the state, and they're just ramping up now. They're just growing because the demand is so great.
Major oil spill seeping into beaches along Orange County. Gallons of crude oil leaked from a broken pipeline.
Our mission is to provide the best achievable capture and care to oil-affected animals, get them back to our purpose-built facilities, and start to get the rehabilitative care that is necessary to get them back into a clean environment eventually.
This is the primary care facility. Basically, an animal starts its journey with us when it is identified to be oiled in the field. I think the biologists are saying the correct pronunciation is plover. So our snowy plovers have been kind of VIP guests on this response. That's because they're federally threatened, and a lot of work has gone into getting their population up and restoring their habitat.
So we're about to do a second wash on one of our snowy plover patients. Sometimes, for whatever reason, they're just not perfectly waterproof after their initial wash. We do think that we removed all of the oil contamination, so it's just a matter of possibly removing more of the solvent that we add to them as the pre-treatment, or removing some of the soap that we may have missed.
I feel that it's a tremendous privilege that I have the job that I have within this response. It feels really good to see that bird fluff up in the rinse, and very soon he'll be released back into the wild because of what I was able to do for him. From the second they come into care, we are doing everything in our power to make sure that those individuals are going to come out the other side of this as survivors and go back home and hopefully make lots of little babies in the future and help their population. So everything we do is designed around minimizing their stress. And I have to say, I think they're enjoying the food here. They have been gaining weight and really going for that food, so that's great to see.
All right, so good morning. So today's day 15 of the spill, day 14 of our response. We're gonna release 5 of our snowy plovers and 2 of our sanderlings. We've got some fish and wildlife specialists coming to band the birds for us. Thank you all. Let's get some birds released.
So now that the birds have come through intake and processing and pre-wash care and cleaning and conditioning, it's now time to do their release evaluations. Our veterinarian is getting eyes on all of these birds to make sure that they're meeting our standards for release and that they have all of those criteria met. And now we're going to be federally banding them and color banding them as well, so that we're able to track these individuals going forward, and we'll be able to know that these animals that went through all of the trials and tribulations of this oil spill response, we'll be able to follow them for years to come.
We just finished banding, so now we're gonna get packed up and make our way down to Huntington Beach and let the birds go.
I think that went absolutely amazing. The birds took a moment to kind of get a feel for their surroundings, and then they flew off. And that's exactly the outcome that we were hoping for.
UC Davis has a pretty incredible reputation for animal welfare and veterinary medicine. I feel very fortunate to work at UC Davis, where we give so much attention to doing things that are good for animals.
UNH is an R1 research-intensive institution, and it is because of investments that have been made all along for many, many years in our research infrastructure that we were able to stand up this laboratory in such a short time and be so successful in advancing this program.
We don't have a med school, we don't have a vet school, we don't have a pharmacy school. We actually did not have a reason to think that we should be able to do this, except we're in New Hampshire and we just do stuff because we know that it needs to be done.
If we weren't doing regular testing, we wouldn't be able to detect the disease in asymptomatic, non-symptomatic individuals.
With this test, we're able to detect really the very beginnings of an infection. And that's getting that spread under control.
And that has really been, I think, critical in allowing us to continue our operations.
The test that we do is what's called an RT-PCR test. So it's the gold standard for COVID-19 testing.
I'm at the center of it. I feel like I'm really part of the solution.
We were able to open, test everybody, have no disruptions, and keep our infection rate below 1% the entire semester. That's the most successful of any university that I know actually in the world.
I think one of the most innovative things that we did was to rely on a self-swabbing protocol. So students get a test kit, faculty and staff as well. They drop those swabs in different locations on campus in secure drop boxes. Our students have been incredibly responsible, and that has been not so much a surprise, but something that we hoped that was really wonderful to see.
The lab, it's a lot of high-tech instrumentation that is very critical to the process, but it's really those people that work in there that have made it work. They are really why it's successful.
I am actually a biomedical laboratory technology major, so this is exactly the kind of work that I wanted to go into. And I knew as soon as the COVID pandemic hit, I just wanted to be involved as much as possible. And I couldn't be more grateful for this opportunity to work in the lab. It's definitely teamwork. We're all working together to fight this pandemic.
It's incredibly gratifying to know that we're making such an impact, both for the university itself and for the citizens of New Hampshire.
You know, it's almost like it was meant to be, and that we just had the right talent in the right place at the right time, and everybody worked really well as a team. This is a signature effort in the university's history that we should all be really proud of.
My name's Alicia Kinoshita. I'm an associate professor in the Department of Civil and Construction and Environmental Engineering. And I study wildfires and their impacts on our water and environment. I'm very familiar with fires and their impacts, and I think we've all seen images of firefighters battling flames and smoke, flying embers, and charred landscapes. And it's these fires that burn the vegetation and that loss of vegetation that create unstable topsoil surface on the ground, which can be moved very easily. So after fire seasons, we get our winter season, which brings rainfall, and that's what starts to move these loose soils. And we see hazards like debris flows and flooding. So in the western United States, fires are increasing in size and severity. And in California, 2018 was our largest fire season on record. And so I think that it's years like 2018 that really highlight the importance and urgency for us to understand wildfires and their impacts. How do wildfires impact our water quality and our quantities? What are the risks and benefits that fires pose to our society and our ecosystem? And then is there sort of this happy medium between public safety and then this need for wildfires that are actually beneficial to our environment? These questions are central to my research and are becoming crucial in light of climate change and population growth, and as people and cities are expanding into fire-prone areas. Burned urban landscapes are becoming a new normal, and they're introducing these new problems. So understanding this new urban fire paradigm is important, and I think it will better help our communities to not only prepare and predict for fire hazards, but also to manage and maybe safely promote wildfire patterns and their impacts.
Science can't be happening behind closed laboratory doors. We need to be bringing people to the table, understanding how our past experience as people on this planet can help us address problems that we face today. My name is Christina Douglas. I'm an assistant professor of anthropology and African studies at Penn State. Where I work in the southwestern Indian Ocean, food is scarce, water that is safe to drink is scarce, and increasingly, as we see climate change intensify, those problems are getting to be more and more acute. I grew up in the Central Highlands of Madagascar. I was adopted as a child. The feeling of being adopted is one of being a child who's taken in, and that's a really powerful way, I think, to develop connections. So to be able to come back as an archaeologist is really powerful for me because it reproduces, in a sense, the experiences that I've had growing up. So in Madagascar, we're working with what some call frontline communities. These are communities who are really experiencing the first really acute impacts of climate change. In the work that we're doing, we're trying to connect the dots in terms of adaptation and in terms of dealing with challenges like climate change in the past. And then we're trying to draw lessons from those different case studies all over the world that we can use to act differently as a global community in trying to address these challenges. Place-based knowledge is essentially the knowledge that accumulates over multiple generations as people live in a particular environment. They learn from it, they transmit that information from one generation to the next. A fisher who's on the team who has a lot of experience can teach us about how to prepare comparative skeletal specimens that we are going to use so that we can actually tell what we're looking at in the past. Even though a lot of members of the team are not literate, they all have tremendous knowledge. So that's why I think place-based knowledge is so important, because it really is that holds the key to addressing these questions that we otherwise would never be able to collect enough data to address. We're taking a step back as scientists, and we're inviting others to take a step forward, in this case specifically inviting community members. If there's one major impact that I would like to have in science and in the world, just as a human being and a member of society, it would be that science will become a much more robust field if we can develop and build on these approaches to inclusion.
I think very smooth to work with Mike from the day one.
I think we're very complementary. I think Chinmay has lots of skills I don't have, and I don't know, maybe I have some skills you don't have. I'm not aware of them. We've been having a lot of fun, and we've also been having our students work together, undergraduate students and graduate students.
So they get a chance of working together in a multicultural environment.
I think we have a bright future.
Yeah.
I think so.
Yeah.
Yeah.
I think a lot of people know that the air pollution in India is generally really bad, but there's less research being done on indoor air quality. Indoors, because people are cooking, they might be emitting different pollution. People might be spraying, for example, hairspray or using different products on their body. We're measuring a number of different pollutants. So one of the things that we measure is particulate matter. So we do that using some low-cost sensors. And so for the sensors, we put one inside and one outside. For the volatile organic compounds, which would be things like formaldehyde and benzene, we actually have some sampling tubes that we set up in the homes. A bunch of the pollutants that we measure, a bunch of the volatile organics, we know are bad for your health. There's a bunch of pollutants that we don't know very much about.
So indoor air pollution is affected by a lot of factors like the furniture, paints, which are specific to indoors. Some of the other sources of pollution can be naphthalene balls, which have been very commonly used, especially in India. We had selected around 20 homes in Ahmedabad and Gandhinagar region.
So one of the things we are doing with this project is trying to catalogue what is happening in India, what compounds are present in Indian goods. I've been vacuuming around the periphery of the main living room, the kitchen, and a spare bedroom, places where we expect to find dust in our own home. The purpose is to look for flame retardants. Flame retardants are in a variety of products, from mattresses to paints to clothes you wear. The expectation is that as India's economy grows, more of these kind of compounds and products that have flame retardants built into them will increase. It's just a matter of first getting the data, and then solutions can be found.
Right now, and especially with the COVID pandemic, there's a ventilator shortage. We've also seen these ventilator shortages in other scenarios, like during natural disasters and in military settings. But basically, there aren't enough ventilators, and so by increasing the number of patients that can be treated with one ventilator, you're increasing the amount of patients that can be treated.
Together with our mentors at Moffitt, we developed a device that could do that in a really unique way.
The UCoVent is a device that allows healthcare providers to co-ventilate 2 or more patients using a single ventilator machine. Our device addresses problems that came up with previous solutions for co-ventilation by giving the patients personalized breaths.
Our device uses a novel time multiplexing approach where the ventilator works double time, but our device alternates breaths between each patient. So because it's alternating, it's effectively like each patient's getting ventilated independently.
This project required work in a lot of different fields. We worked in coding, we worked with a microcontroller and a lot of electronic components. We worked with designing things on SolidWorks in CAD and 3D printing them. Being a biomedical engineering undergraduate, this project really merged the two concepts of medicine and engineering.
The end goal, of course, is to get the device to the clinical setting so patients can actually benefit from it.
To have that impact to potentially save someone's life, it's a really cool feeling to have, and that's why I definitely got into biomedical engineering.
Typically we hear climate change and we think about icebergs and these ice sheets. It's this very far away problem, right? We have some psychological distance to it. And I sort of was in the same boat, so to speak, until I went to Greenland and Alaska and realized that for some people this is their life, right? The people there depend on the fjords for their life, both culturally and for food. My name is Dave Sutherland. I'm an oceanographer at the University of Oregon in the Department of Earth Sciences. And I study places where freshwater meets the ocean because these are the really interesting places that humans live around and, importantly, that climate change is affecting. In 2008, I went to Seelik in the southeast part of Greenland for the first time, which is a town on Sørmelek Fjord, and actually tried to collect the first water measurements. And so we get on this really small boat, and we were like, whoa, this is our research vessel? Pack all of our instruments on. And so we went out of the harbor, around, and you sort of have to navigate through these rocks. And you come around the corner, and then it just sort of hits you. There's just these mountains of ice all around you. And we're navigating in our tiny 20-foot boat around these icebergs, just looking up in awe. It just puts things in scale and how much ice is coming off these ice sheets. When we talk about climate change, one of the really big factors is how much sunlight Earth reflects back up into space. We say it's about 70-71% ocean. But then, what I don't think people think about very much is a lot of the land in the ocean is covered in ice. And so that means that the ice, the cryosphere is what we call it, is really important to understanding Earth's climate because it reflects the sunlight so much more than these other types of land or ocean. And so as we move forward with climate change and we reduce the footprint of the cryosphere on Earth, lose that ice reflected ability, we're going to absorb more heat, and that just feeds back on itself. Those glaciers are actually putting fresh water into the oceans 2 ways. So one way they do it is just by melting. It's like pouring water into the oceans. If you do enough of that, you're going to raise the global sea level. The other way they put fresh water into the oceans is via icebergs. It's like plopping an ice cube into your drink. You can see the level of your drink go up, but as that iceberg, in this case your ice cube, melts in your drink, the level doesn't change anymore. And it's a totally natural phenomenon. But what's happening recently is that more ice is being lost than what's being replenished. The physics of it is really simple. We can actually compare it to a bank account. The snow is like the money you're putting in. If you build up enough of that snow, it actually has enough pressure and weight that it pushes down and compresses and turns into ice. If the snow you put in every year doesn't keep up with the amount that you're spending, your bank account is going to shrink. And that's what's happening right now to the Greenland ice sheet. And that's just not sustainable. So here's an experiment you can try at home. Take 2 cups of water, take some salt, put salt in one of those cups, make your own ocean, right? So now you've got an ocean in a cup and you've got your fresh water. And then put ice in both those cups. Before they start melting, make a prediction. Try to decide which of these cups is the ice going to melt faster. Go off and do something else for 10 or 15 minutes. Come back, and you should see right away which of the cups has the ice melted faster in. In the saltwater cup, when you add fresh water via the melting ice, that fresh water is actually less dense than the salt water. You can imagine like if you put oil on top of water, right? The oil is less dense than the water and it floats on top. And in the ocean, that's exactly what fresh water does. So as it melts, you're basically creating this little surface freshwater cap that gets really cold and it actually protects that ice from melting even further. Whereas in the freshwater cup, as you melt that ice, it becomes cold, and cold water is more dense than warmer water. And so it actually sinks to the bottom and you actually create this really cool convective current. And if you want to visualize that current, you can actually get food coloring and put a little bit of dye in each cup. And you'll see that the dye in the freshwater cup actually sinks to the bottom and sort of starts moving around in a vertical fashion. Whereas in the saltwater cup, it just sits in that surface layer. And this illustrates a few really important points about the real world ocean. One is that the ocean has density structure. You don't just have fresh water on top of salt water, but it's got many, many layers. You can kind of think of it as this layer cake of density of different water masses. And that gives us a hint as to how the ocean circulates water, heat, nutrients, and organisms. If that didn't happen, then the tropics would be warming up all the time and the polar regions would be just getting colder all the time. There's this effect called polar amplification. The polar regions are warming much faster than anywhere else on the world. And everywhere around the world, the temperature is increasing, right? And that's not a surprise. Everywhere except around the Greenland ice sheet, actually. And that's a direct effect of the more ice that's coming off the Greenland ice sheet. Why they're interesting to me is because oceanographers haven't really studied them because they are ice. And glaciologists don't study the icebergs because they're in the ocean now and they're far away from the glacier. So they're these really monstrous icebergs that kind of create their own ecosystems. And no one was really studying them for the past 10, 20 years. And so I think it was this gap in the knowledge of how they're impacting the world's oceans, how they're impacting the climate, how they're impacting the marine organisms and ecosystems that they travel through. And so all of those are really active areas of research that are all really important.
My name is Cecil Lewis. I'm a professor of anthropology here at the University of Oklahoma. And the project that we're going to talk about is the Chomper Project, which is a project that's trying to understand ancient oral pathogens. So we know that cavities that you might suffer from in your mouth, we know that they affect about 3.5 billion people around the planet, 50% of the world's population. And in that sense, it's essentially a silent epidemic. We know how to prevent it by oral health care, and yet it's still ever present.
So what we're hoping to do in this project is look at how the genomes of the bacteria that cause some of these important oral diseases have changed in respect to the species that they infect, host geography, time, and then dietary lifestyle. Using something known as shotgun metagenomic sequencing, what we can essentially do is get the entire genomes of all these bacteria that were present in these ancient dental calculus samples. And then you can look at how have those genomes changed over time and with these different dietary lifestyles. So do you see the bacteria becoming more virulent? So do they cause more and more severe disease? Do you see more evidence that they're gathering genes that can help them survive in this changed oral environment?
I think one of the really exciting parts of the project that we're doing is that while the science is really interesting, we're doing ancient DNA in one of the largest ancient DNA labs in the United States. But I think what's also very exciting is our partnership with descended communities and the very samples that we are using. So it's not just taking a sample and having it within the lab and only looking at the lab. It's actually engaging in the communities who are stakeholders, who are descendants of the very populations that we're examining through ancient DNA.
I was fortunate before I came to Rockefeller to teach at San Quentin State Penitentiary, and I taught there through what's called the Prison University Project, and there I met students who allowed me to sort of understand the joy of education and the joy of thinking original thoughts. I was inspired by that experience, and I saw that and I thought how much that impacted me, and I wanted to pursue further education. We learned from the very beginning that having original thought, having new ideas and tackling new ideas is the bread and butter of our future as scientists. For me, the motto, science for the benefit of humanity, is a major reason why I chose Rockefeller. We're lucky as scientists to be interested in a lot of things. We have labs here that study how dolphins communicate. We have labs here who study the social behavior of ants. We have labs that study neurodegenerative diseases. All of these things are super diverse, but at the same time they're focused on this mission, which is eventually benefit to humanity. I took a flight from New York to Seattle on the way to a conference, and the guy next to me asked me what I did, and we started to have a conversation, and I started to explain to him about HIV and the kind of research that we're doing here, and he thought about it and he was quiet and he asked a lot of questions, and then about 2 hours into the flight he reached into his vest pocket and took out a big red pill, and he showed it to me and he said, "I just wanted to tell you that I'm HIV positive. This is the medicine that I take every day. I appreciate what you're doing. Thank you, keep going, we need you." Meeting somebody who's affected by the thing that you think every day, all day about was really pretty special. I think that was a big motivation. Being here at Rockefeller and seeing the motivation of everybody around, it's sort of like a big wave and you ride it with everybody else. There's a misconception that doing science is a solitary endeavor, and that couldn't be farther from the truth. Everything that we do at Rockefeller and as scientists happens because we have a great team of people. I do believe that within science especially, but in all fields, that diversity really matters. Diversity in science gives the ability for the group as a whole to see that problem from all the different perspectives of all the different people. When you limit the kinds of people who can attack a problem, you limit the kinds of answers that you might get from that problem. Nothing that I've accomplished happens because I worked alone hard in a lab. That feeling of discovery, that feeling of I just learned something that nobody knows, it happens and it's yours for a moment, but then you share it with your lab mate and you share it with your mentor and you share it with the greater scientific community, and that feedback allows you to get to that next moment of discovery, that next insight. All of it happens because you have a great community around you.
Hi, my name is Jillian Gloria. Oh wait, there's frozen water. Uh-oh. We have a psychedelic moon now, hold on. Hi, my name is Jillian Gloria. I'm an aerospace engineering student at UCF, and this is my research in 60 seconds. Water is essential for life as we know it, from the air we breathe to the water we drink. H2O is key. And as humans look into building permanent habitats on the moon, water is the one thing that is mission critical. We know there's frozen water located at the poles of the moon, but there's also been evidence of hydration across the entire surface. But what kind of hydration? Is it actually like water molecules that we drink every day? Or something more like drain cleaner hydroxyls? That's where my research comes in. This is moon dirt, and it's made up of a significant amount of aluminous silicates. To understand what type of hydration is on the surface of the moon, we bombarded samples of this mineral with different forms of radiation to simulate the effect solar wind has, which in turn caused a chemical reaction and water to form. Our experiments proved how water evaporates on the moon, which provides NASA with a better understanding of where the water is so we can send our astronauts to live and work safely. And that was my research in 60 seconds.
Think about the electricity. it's almost always there. You use it, assume that it's going to be there. This is not because it is something simple, it's very complex. In North America, we can think about billions of the components in the power system. Also think about how do we interact as a human being with the power grid. That makes it more complex. You turn on the light, you turn it off. Actually, that is kind of interaction with the power grid. It may cause the frequency goes down a little bit, and the generator may sense it and pump more energy into the power grid. It's like it has life, going up and going down during our daily life. It's like a living being. The situation awareness is mainly for the power system operator, for them to know what's happening right now, what's going to happen in the future. Because power grid is has a response time that it takes time to ramp up the generator. You have to let the generation know ahead of time so that they can be prepared for that. The situation awareness is critical in that perspective. Without situation awareness, a lot of power system engineer tends to be conservative. That means they want to make sure the power grid will survive any events. They try to minimize the risks there. Sometimes more conservative than necessary. That means a lot of customers will lose their power supply. On the other side, because you do not know what's going to happen, you have to do that to guarantee that power grid will survive major events there. And with my research, we are trying to provide not only the good current view, but also what's going to happen in the future. Then, the power system operator can operate the system to the best operational point. That means they will keep as many as consumer as possible in their grid, and at the same time, maintain the reliability of the power grid. That is what my research is going to contribute to. My name is Ning Zhou. I'm an associate professor with the Electrical and Computer Engineering Department.
So our laws of physics can explain the 5% of stuff that we know of. But to explain the missing 95%, we need something that goes beyond what we know already, beyond our current laws of physics. I'm Jo Dunkley, and I'm a cosmologist. Cosmology is the study of the universe as a whole thing. It means trying to understand how it began, what it's made of, how it's got to be where it is today, and what's going to happen to it in the future. So when we look into space, there's no reason why the things that we see should be all that's out there. You see the bright lights of the stars, but there may be something more. One of the reasons that we've come to know there must be something out there is that actually we can weigh the whole universe. We can actually weigh, on average, the whole of space. As cosmologists, we've actually done that. And then you can go and look and see what you can see with your telescopes. And you can match those up, and you find that there's a piece missing. What we can see, matter that we know of, that we are made of, particles that we know of, is only 5% of the total stuff that's out there. So we give this 95% of stuff two names. There's a part called dark matter, and there's a part called dark energy. The dark matter seems to be an invisible particle that feels gravity, but doesn't emit any light and just, could just pass straight through our body without noticing it. Dark energy, on the other hand, which actually makes up about 70% of that total, is really mysterious. It's stuff that seems to be making space grow faster and faster. It might just be the energy of empty space itself, but we're really not sure if that's what it is, and we don't really have any kind of understanding of why it should be there. So one of the ways to try and see invisible things is to look at distant light and see how that light is affected by the invisible contents. So what I do is measure light that set off 14 billion years ago and is travelling to me now. I'm reaching it now. But on its path, it's encountered all this invisible dark matter on its way. And the more of it there is, the more of it actually bends that light's path from the gravity of this invisible matter itself. And so we can look at these incredibly distant rays of light, either coming actually from distant galaxies or from the very beginning of the universe. And we can see how much it gets bent by gravity. And then we can infer where and how much of this stuff there is. As an example, if we had no dark energy, things would tend to collapse in space more often. You would get big cosmic structures of galaxies and clusters of galaxies grouping together and growing bigger and bigger. So one of our goals is to look over this sort of billion-year history, how these giant cosmic structures of clusters of galaxies, how they have grown and whether and how this dark energy seems to be spreading them apart. We don't know how big a deal this is. Dark matter could just be a new particle that could then fit in as a fairly minimal extension of the standard model of physics. In solving dark matter and dark energy, it might be something bigger. It might be something that would lead to an entire paradigm shift in our understanding of physics. So we're looking forward to many new telescopes in the 2020s that will look for this invisible stuff in different ways. So our main goal is to see how light from distant objects gets bent by the gravity of all this invisible stuff to try and work out what it is. And so big new telescopes coming in the 2020s are going to measure billions of galaxies, and we'll look how the light from them is subtly distorted by this invisible stuff. And we're actually going to measure light even from before there were galaxies, from the beginning of the universe, the most distant light of all, and see how that's been bent by all this invisible stuff. I'm Jo Dunkley, and I'm a forward thinker.
I've got a creation story to share with you. A story about how a great university came to be. It starts with an almost magical substance that the colonial pioneers called hardpan. Hardpan is made almost like spreading crunchy peanut butter on bread, except that the butter is made of wet pulverized rock and the crunchy bits are leftover stone. This stuff was pressed and pasted to the land surface on the bedrock by sliding glacial ice, which also shaped the land into beautiful hills like this. The climate changed, the ice melted, and tall trees grew from seeds like this. And then English colonists came in 1698, especially Samuel Storrs. You know what he did? He chopped down those trees so that he could expose the rich, beautiful hardpan soils. And they were particularly good for growing grass and grain, which kept the Storrs family farm successful for many generations. In 1881, Charles and Augusta Storrs donated the family farm to found a small agricultural school. This school became a state college and then an international university. But let's not forget that the creation story of Yukon Nation began with a soil made from ice and rock. That's where this ice cream really came from.
I couldn't have gotten where I am without really kind of leaning on the community, without asking for help sometimes. I think we should never be afraid to ask for help when we need it, to ask for support, to look for collaborations, and having, just really trying to build that community. I think that's really what has supported me throughout my career. Molecular animation, I think it's been really fun. I think mostly because we get to work with such great collaborators and think a lot about really diverse science. With molecular animation, what we're doing is we work together with scientists to create visualizations of hypotheses. These visualizations are animations typically, and they result directly from the ideas of our collaborators. For example, we've animated the HIV life cycle, we've animated the SARS-CoV-2 life cycle. We're interested in using animation to try and get an understanding of how close are we to a community consensus on how things work at a molecular scale. One of the things that I think has been really interesting about animation is that it allows people to understand where their differences lie. So when I've shown animations or I've watched a collaborator show animations within a talk, there are people who stand up and are like, no, that's not the way it works. I have a different idea. And they're able to communicate that idea in a much more exact way that was really allowed because of that animation. That should be part of the joy of creating this is kind of the technical challenge of thinking about how to do this, but also that at the end you have something that really shows an idea that has never been communicated quite like this. We meet every week. I started talking to people in my department about starting a group, an animation lab, where we could take on more and diverse projects, and I could also start training people to take on the type of position that I have here. My lab right now is 6 people, so we have a number of postdocs and we also have a full-time animator. Grace is from Canada and Taiwan, Shraddha is from India, Anne is from China, Margot is from France, and Francesca is from the US and Puerto Rico. Everyone has different ideas and can give really great feedback to each other about how to improve our visualizations. These animations that we're creating, nobody's ever created an animation that shows this exact thing. We really have to come up with these solutions ourselves. I enjoy having a challenge and also doing something that's new, at least to me. I think one of the things I really like is being able to work with my hands to create something. I think that offers some balance from just sitting in front of a computer all day. Every year I ask them, what they'd like to be for Halloween. Aki, my oldest son, he asked to be a flying squirrel, which is one of his favorite animals. So I made him a flying squirrel outfit costume. And Kenzo, he recently got a pet snake. And so he really wanted to incorporate this snake into his costume, and so we're making him a snake handler. I'm happy when they try to give me a difficult one, because I'll try to do it. I'm always up for a challenge. One of the great things about being here at the U has been a really diverse community that I've been able to connect with over the years. There's this real, kind of sense of community here that goes beyond any single department, and that's something that I've really appreciated. I don't honestly know whether that would necessarily happen anywhere else. One of the things that I thought about when starting the lab was the lack of opportunity for people who are interested in this type of work. So when I was a postdoc, I was really lucky to have an opportunity to do animation full-time, but opportunities like that really just don't exist. And so I wanted to offer that through my lab, and so I think it's really one of the few places in the world where postdocs are able to get this type of training. This is my dream job, and I'm hoping that they can find their dream jobs and that I can help them get there.
everybody who knows us knows that we are very different. I am talkative and bubbling, and Drew is more scientific. You are coming from A to B in a straight line, and I am A to B like that. You told me that.
Yeah.
But we try to go to the same place.
It's actually funny the way Katie and I met. Back in those days, the only way you could read journal articles is you had to photocopy them out of the journal. And we would fight over the copy machine to be able to read articles. And we started talking and comparing what each other did.
I was working with RNA, and I learned all of the immunology from you.
We started working on RNA to try and understand why it was so inflammatory. We were both completely open-minded. Any data that we didn't understand, and there was a lot of it, we sat down, we kept doing experiments, we kept getting results, we kept getting excited by the results.
Middle of the night, submitting grants, and 2 o'clock, 3 o'clock in the morning, sending each other, and you are still up, and I am still up.
We couldn't have come to the result without both of us being involved.
I was making the RNA, and Drew was checking whether it is immunogenic, not immunogenic. Then he got the data, and we leaned over, and we try to understand and make sense of it.
Finally, we figured out how to make it non-inflammatory.
And then our mind was all over the place.
Just going in every direction, thinking a year in the future.
We just were amazed that, oh my God, this is what it means.
And after that is when the vaccine field and other RNA fields took off.
Coronavirus officially hitting the U.S.
Cases here in the U.S. have exploded. All-time highs today in many locations.
When we started this, we weren't thinking about curing pandemics. We were thinking about making new vaccines. We had 5 phase 1 clinical trials of different mRNA vaccines that we were working on before COVID-19 ever hit. And we knew at that time that this had the potential to be an incredible vaccine.
Moderna already tested influenza vaccine, which was mRNA vaccine, 2 years before. It was just the public didn't know about that.
One, 2, 3. You will not believe how happy I am. Yay!
Seeing the phenomenal success of vaccinated people being protected gives me incredible amounts of joy.
I was really happy when people wrote me emails and said that they could see their parents and family members. They could meet each other.
We haven't thought of all of the things you can do with mRNA. My family, and I'm sure my lab, is mad at me that I didn't celebrate when the phase 3 clinical trials came in. I had already moved on to something new. We were working on pan-coronavirus vaccines, sickle cell anemia gene therapy, malaria with people across the US and in Africa, leptospirosis with people in Southeast Asia, vaccines for peanut allergies. We're working on really every imaginable infectious disease.
I was always interested about this fragile molecule, this RNA, and still today I am following scientists discovering new things, and I am just fascinated, just like an exciting crime story, and I am so glad that it eventually helps humanity.
I never sit back and rest on laurels. I'm always moving forward. I'm always moving on to the next disease, the next vaccine, the next therapeutic. And that's just the way I think.
We worked together a lot, and we had a lot of fun.
It was a lot of years, but they weren't boring years.
It was very enjoyable. To be a scientist is a joy.